In this lecture, we will discuss problem formulation. Okay. So, a little collection of problems I have kept. They are mostly simple and fairly general for a diverse audience to follow easily. So, first of all, what is problem formulation? We have discussed it one round earlier in the second lecture, optimization problems. Now here this lecture is devoted to this discussion. Okay, so we need to first study the problem carefully, making note of all the relevant facts and issues, whatever minor they may seem. Out of that study, we need to identify variables and parameters, objective function, and constraints, if there is any. Now, next, organize all these elements in the standard structure of an optimization problem. Minimize this function of these variables subject to these constraints in that manner. Now, explore the boundaries of the system, what will happen in this extreme case and in that extreme case and so on, and ensure that all eventualities are provided for in the formulation. Conduct a thorough scrutiny that everything in the formulation makes sense and there are no loose ends. This much is the beginning which you need to do from the knowledge of your own field. And it is important to do this carefully, do this well. You owe it to yourself that whatever problem you are going to solve, you formulate it thoroughly, and then the optimization methods that we discuss in the course will be actually used or be useful. So in what follows, we will discuss some fairly general problems and their formulations. First, we take some trivial problems. Say an airline allows a suitcase as cabin luggage and does not require it to be booked if its size is within the maximum allowable size. And how does it define the size? The size is defined as length plus breadth plus width. Okay, three perpendicular dimensions. Actually, I have traveled in such airlines. Okay. Now, you want to carry the maximum amount of your things in your suitcase in so far as size is concerned and volume. Basically, you want to carry maximum volume. Okay, uh, and want to fit within cabin luggage. So what will you do? How do you formulate this problem? This problem is trivial. How do you formulate this problem? You formulate like this. Maximize the volume, which is LBH, subject to the size. Actually, L plus B plus H less than equal to L. But since you are interested in maximizing this, it's obvious that you will try to make it equal. Okay. So equal to this, where LBH are non-negative numbers. So solution will be even easier. You know that it will be a cube. Okay. But a cubical suitcase may not be a great idea. That's a different thing. In a variation to this problem, there may be another airline which says that no, our definition of size is the length plus the perimeter on the other plane, okay, perpendicular to the length. So in this case also you can work out a way to carry maximum volume. Okay, so you work it out and check in what manner it differs from here. We come to another problem that is also trivial. Take an A4 sheet and from all sides fold equal width to make a basket. Okay, rectangular basket. So from all the four sides, you fold a little amount, say W width, to make a basket. Now, how do you maximize the volume of that basket? If you fold too little, then the height of the basket will be so less that not much volume will come in that. On the other hand, if you fold it too much from all four sides, then area, the horizontal area of that will turn out to be so small that not much volume will come. Okay, so you need to hit the balance. In between some width you should fold so that all dimensions are reasonably respectable. Okay, so what is your formulation? You may make this formulation: maximize volume, which is L minus twice W into B minus twice W into W. Okay, fair enough. This is the length after folding from both sides. This is the breadth, and this is the height. Okay, so is your formulation like this? If it is, then it is incomplete. And later, after solving and trying to present the solution, or during the solution, you might have an occasion to say, well, you see, this obviously doesn't make sense, so this kind of thing is excluded. It's not a great idea to formulate the problem, solve it, and then while presenting the solution, explain why something in the formulation did not make sense and therefore you discarded such a solution. No, it's better to do a formulation which is neat. So for that neat formulation, this is correct. There is no doubt about this, but it is incomplete. So something more has to be put in the formulation. Right now, we see this is one constraint, W greater than or equal to 0, obvious constraint. Now there are two other constraints which should have been equally obvious. Twice W should be less than, or it should be L, not H. Twice W should be less than L, and twice W should be less than equal to B. Less than equal to L, less than equal to B. Because more than B by 2, if you fold from both sides, then the paper itself loses all its breadth, right? So, I mean, this is a very trivial kind of example where a slip, an oversight at this stage may create later problems. And in this case, if you do not include this 2W less than equal to B, then you are actually going to run into trouble when you put the dimensions. Say you put length equal to 30 centimeter, width equal to breadth equal to 21 centimeter, then one wrong solution tends to turn up in your consideration, and then you have to say that in that case W is too much, that is impossible, so we try to get a monstrous calendar basket, so we get rid of it. Okay, in any case, that was going to be a minimum volume basket if the volume was negative, so you can check that. Now we come to actually a very famous problem, easy but very famous problem, in the sense that it was proposed in the medieval period. Okay? Not exactly in this manner, but in some other context. I have organized the context. The 5-year-old child of a science teacher is fascinated with her father's study and keeps roaming around there and keeps looking at the periodic table chart hanging high on the wall, likes it. Okay? How far from the wall should she stand to get the best view of the chart? Obviously, the chart is completely above her head, okay, because she is a child, small child, and the chart has been put on the wall for adult view. Okay, so the entire chart is above her head, and she has to look upward to see the chart and read H, HE, LI, and so on. Okay, periodic table. So, how far should she stand to get the best view? So, for the best view, the chart should subtend the largest angle at the eye. So, this is a child, this is her eye at the height h from the floor, and this is a picture. This is a chart. Okay. So Mn is the chart, and the angle the chart makes at her eyes, that is say phi. This angle is what you need to minimize. Okay, sorry, maximize. And what is the variable for that? The question is how far from the wall should she stand? So this distance OA, this is the only variable x. Okay, so the height of the top edge of the chart, bottom edge of the chart A and B, these are parameters. H, the height of her eyes, that's also a parameter. So you want to maximize this angle, which is angle MPN. Okay, and that is the difference of MPQ and NPQ. Okay, the two red angles that are shown here. The difference is this phi. So phi is this angle. And formulation is over because these two angles now you express in terms of x. Angle MPQ, this angle, okay, that is A minus H by x tan inverse. So this. And the other angle, the smaller angle, which you need to subtract, that is B minus H by x tan inverse. Okay. So this is all. This you have to maximize for non-negative x. Okay. So this is easy. But at this point, the formulation is over and your method. It may be analytical. This problem can be solved analytically. Okay. It may be analytical, it may be computational, iterative, or whatever. That is later. First, you need to formulate the problem completely so that it is well defined, well posed. Now, another problem which is common about product mix. Okay. I have defined a kind of problem which is individual problem for one person. Such problems are often encountered in shops, okay, to maximize the productivity and efficiency of the shop, okay, in big businesses also. Here we have an apprentice tailor who takes 2 hours to completely stitch a shirt, of which 1 hour has to be at the sewing machine, which is possible only at the shop. For using the sewing machine, she has to go to the shop. So 1 hour there is must. The other hour that she needs to complete the shirt, that she can do in the shop or at her home. Okay, it's up to her. Similarly, she takes 2.5 hours to complete a pair of trousers, which includes 2 hours of machine time, for which she has to go to the shop. Now, what is her payoff? She gets rupees 60 for each shirt and rupees 90 for each pair of trousers. Very underpaid, but let us concentrate on the problem. In a week, she can work for 50 hours at most, and she can engage a machine at the shop for at most 36 hours because the machine shop will be closed. Okay, but the rest 14 hours she can work in her house. Okay, even late night. Okay, so for how many shirts and pairs of trousers should she try to collect orders so that she gets maximum income in a week? So if the time constraints were not there, then she would collect orders only for trousers, okay, as many as possible. So that is sort of meaningless, but there are constraints. Okay, so you put everything together. Number of shirts S, number of pairs of trousers T. So if in a week she gets these S shirts and T pairs of trousers orders, then this much she will earn in the week. That is her income, which she wants to maximize. What are the constraints? For every shirt, she has to give 2 hours. For every pair of trousers, she has to give 2.5 hours. The sum total of that cannot be more than 50. Similarly, machine hour, 1 hour for every shirt and 2 hours for every pair of trousers. That cannot be, total cannot be more than 36. And of course, S and T both should be non-negative. So this is formulation complete. Easy problem, you can actually solve it. and you do not need to calculate much. You can just do it graphically. This problem can be solved graphically. You can solve it by numerical methods also, and that we will cover in the course. But this is easy. Two variable problem you can solve graphically. But right now we are not discussing solutions. Okay. Now, a geometry problem. How to determine the closest distance between two triangles ABC and PQR? The position of all the six vertices A, B, C, P, Q, R are known. So if you take one point from triangle ABC, another point from triangle PQR, then you can evaluate their distance. Now, how to select a point there and a point here so that this distance is minimum? If the triangles intersect, then that minimum will be 0 actually, but in general they may not. In space, you can place two triangles which don't intersect. Okay, so first we need to model the position of a general point in a triangle. In a triangle, there are infinite points. How to address each one of them? By coordinates. Okay, so there are many ways to do it. Okay, one very straightforward way to do it is using the so-called barycentric coordinates. Okay, in that, if you model the triangles, then a general point in the triangle ABC will be like this, a convex combination of the three position vectors, convex combination. So each of them is non-negative, the sum is 1. Similarly, a general point in triangle PQR is V, which is the convex combination of coordinates of P, Q, and R. Okay, the position vectors of P, Q, and R. So like this you put, and then you want to see the distance and its magnitude. So that is the thing that you want to minimize. Okay. So either the distance itself, or say its square, or say the half of its square, it is the same thing. That half is not necessary. Okay. But later in solution, it helps. I mean, it helps in a trivial sense, but we often keep that half. Now, the basic task of formulation is actually over, but you can consolidate the formulation and put it in a nutshell. So, put all the variables in a vector together. Okay, so u minus v turns out to be like this, and these are the transpose here should not be there, no? Because x1 times a, yeah, this transpose is wrong. This transpose should not be here. Okay. So it is just this matrix, 6 columns and 3 rows. Okay, so transpose is wrong, should not be there. So H will be a 3 by 6 matrix, and that's a constant matrix. It just has the 6 coordinates, 6 vectors. Okay, so 6 into 3, 18 coordinates of the 6 points. Okay, that will be the content of the matrix H, and it's constant. So the complete formulation will be minimize half this thing transpose this thing. Okay, so that is this. Okay, half x transpose hx, subject to the constraints. Altogether, you put these constraints come from the requirement of convex combination, right? Now, a little serious, difficult problem taken from a paper actually. Okay? This figure shows an automated device for fine manipulation of the position and orientation of a platform relative to a fixed base. Okay, and you have 6 extensible legs where you have linear actuators. Now, when there are some external forces and moments on the platform, the linear actuators will accordingly get loaded. Okay, and now it may happen that if the forces and moments are in some directions, then there will be one load distribution, and if they are in other directions, similar magnitudes, then the load distribution may be something else. And this load distribution may be seriously uneven. Okay, that is in some direction, that is in some actuator, a lot of load may have to be taken, while the other is not sufficiently loaded. Okay, so this kind of situation may happen. Now, how to minimize that unevenness? How to position the 6 points on the base and 6 points on the platform so that for forces and moments coming on the platform in all directions, none of the actuators are severely loaded and none of them is left totally scot-free. So that basically you are telling that such that all the actuator loads should be comparable. Okay, so that is the problem. Place the platform at its now. That is the problem. How to locate the 12 connection points, 6 on this and 6 on this, so as to minimize this unevenness of the 6 actuator loads. So now the platform will move around, but in its workspace, find a central location at which you try to make the best design, and around it will be close to that. Okay, so place the platform at its reference position and orientation centrally in the workspace, and express the external forces in terms of the 6 actuator forces. You can see that in terms of the 6 actuator forces, you can actually get the resultant here, and that should be equal to the external force and moment. And all the forces are in this direction, in the direction of the leg, because here is a ball and socket joint which will not transmit any moment. Okay, so based on that, as you express the force and moment at the platform as the resultant of these 6 forces of directions which come from the connection points which you are going to design actually. So you put it like this: force moment on the platform, and that force balance moment balance, when you consider they are linear in the forces, so all the 6 scalar equations, you will get linear equations in f1, f2, f3, f4 up to f6, and you can organize like this. This matrix H is the 6 by 6 force transformation matrix that depends on the geometry of the device. That is, where are the 6 connection points at the base and where are the 6 connection points at the platform. Okay, this matrix H is something that we are really trying to geometrically design. Okay, so the unevenness of this mapping is given by its condition number. It is a straightforward linear algebra construct, which is sigma max by sigma min, the ratio of largest singular value to smallest singular value, that you can evaluate if H is given. And for H to be given, you need to have the 12 connection points, 6 at the bottom, 6 at the top. Okay, so the 36 coordinates of these 12 points are actually housed in the big vector X. So it's a 36 variable problem. Okay? So this is what you try to minimize. The minimum value, the at all possible minimum value is 1, because that will happen when max and min are same. Okay? All the singular values are same. But in the case of this structure, that is never going to happen. So whatever is least, 5, 7, 10, you will accept. But you want to tweak around with the positions of the 12 points so that you get the least. Okay. Any constraints? Yes. All the points should not come very close and the points should not be too far away. Okay. So such mundane constraints you have to formulate and put together. Try to spell out and enumerate what constraints for the XYZ coordinates of the points you should have. And this is the reason why in the picture you see there are dimensions given, length, breadth, and height for this also, length, breadth, and height, so that you do not try to put connection points outside that. Okay, so connection points should be within some bounds and they should not come too close. So these are the kinds of constraints which you need to quantify and put in that formulation. So then you will say with this x 36 variables, with this definition of h, doing the vector products and assembly, then this function, by writing a function to evaluate this condition number, then you will say minimize this subject to constraints which you work out from here. Okay, so you do it and see how it comes out, and if you want to check your answers, you can consult the reference which was given here. Okay, Sadhana 2011, this is a journal, so this is actually from a published paper. Okay, another interesting problem: what will be the equilibrium shape of a chain of n uniform links, each of length L, when hung from 2 points on the wall? The relative position of one point from the other has been given with this. One is, suppose you can consider as origin, other is PQ. So horizontal distance P, vertical distance Q. Okay. Of course, total length of the chain should be greater than P square plus Q square under root. Otherwise, there is nothing to solve. If it is less than that, then it is not possible. If it is equal, then it is straight. So it doesn't matter. It doesn't make sense. So only with this, there is a problem in hand. Okay. So now the formulation. If the ith link has a signed vertical projection yi, that is, if the link beginning to link end is going upward, then this is positive. Otherwise, in the other case, it is negative. So it has to be signed. Okay. Then its horizontal projection is this, you get from Pythagoras straight. And the vertical position of the center point will be the sum of the previous ones, including this one, minus half yi. If you sum up till the previous one, not including the current one, then here it will be I minus 1 and this will be plus. It is the same thing. And then based on the center point, you work out the total potential energy. Okay, mg yi bar. Then put this yi bar here and you get this. Okay, there is a double sigma, double summation. But it will get reduced to single sum. Okay, because you, as you say that for I equal to 1, what will come, for I equal to 2, what will come, and so on, then you will notice that y1 will come in all of them except its own, in that just half y1 will come. Y2 will come all but the first two plus half y2 in itself, and so on. Okay, so like that you can just go a little inside it and find out that this double summation comes as a single sum like this. Okay, this is the total potential energy which you want to minimize. Okay, so for the equilibrium configuration, we try to minimize. Now mg I have thrown away because it is constant anyway and common. Okay, so this is a linear function. Okay, some coefficient into the variable and so on. Like this, there are n variables which you want to find out, and there are constraints, the n positions. Okay, the total vertical distance, total horizontal distance. Okay, so minimize this in these variables y, subject to this constraint and this constraint, and that's it. Okay, now there can be an extension of the problem. If you go on making smaller and smaller links and more of them in number, that is reduce L and increase N continuously with the same product being the same indefinitely. Very small links and many of them. Okay. Then finally, the chain problem will be replaced by a rope problem. Okay. Each infinitesimal length and infinite lengths like that together. Okay. So all these three summations will then be replaced by appropriate integrals. Okay. And then rather than n numbers, y1, y2, y3, y4, you will be actually looking for a function y of x. Okay. And the problem will be of variational calculus. There are ways to solve it. I mean, quite interesting. And as solution, you will get the curve called catenary. So catenary is the curve which gives you the shape of the rope hanging from two given points on a wall. Okay. So try it out, and it is interesting problem. One more problem we see how to formulate in this lecture. What will be the shortest total distance of travel for a salesman to visit each of n towns of known locations, or in a single city also it may be n places, okay, in a cycle. Okay, so he has to come back to the starting point. So the solution space actually has n minus 1 factorial cyclic permutations. So if you number the towns in some manner 1 2 3 4 5 6 up to n, then every cyclic permutation of that, okay, starting from somewhere and ending there by visiting everything else once, that's a permutation of these numbers. So each such permutation is a solution, a feasible solution. So among such permutations, he has to actually get the best permutation. Okay. So I1, I2, I3, I4, say this is a permutation. If you include in plus 1, which is not there actually, as equivalent to I1, then you can concisely write the complete length. Okay. Succeeding minus previous size length. Okay, that is this. And this sum you have to minimize, that's all. But solution is quite complicated. Okay. Now, this is complicated enough. And traveling salesman problem is a very famous problem. Okay? Now, this is complicated, and there are some algorithms to solve them. Okay, and you can experiment with them. Okay, so the complication may increase if the distance gets replaced by some cost function, which is complicated. Okay, so it may be the cost may be something else, not just distance. Okay, and this is one of the most celebrated problems of combinatorial optimization, and most probably it is the first problem which got formulated in the area of combinatorial optimization. And many other problems in some way fit in this framework. Okay. So in this lecture, we have seen a few examples of problem formulation. And now to summarize everything that we have discussed, make note that a problem formulated is half a problem solved. Okay. That is why you should formulate the problem reasonably well. And in the formulation stage, due care should be given to all the issues, avoiding oversights. Here, I have considered only fairly general examples, keeping in view diverse audience. But in your own field, when you come across suitable problems, you should be able to spot them. Okay, that this is a problem of that kind. Let me try to formulate it in this way, and so on. Okay? And in the formulation, it will come out how well educated you are in your own field. Okay. And there is one more thing which is not so well appreciated, is that prior knowledge of solution methods for a kind of problems increases your chance of formulating the problem in the first place. Otherwise, even if you know the subject matter of your own field very well, if you don't have a priori knowledge of how to solve certain problems, you are very unlikely to formulate a problem of your own field in a form in which you don't know how to solve the problem. You don't even know whether the problem in that form can be solved at all. You are unlikely to formulate that problem. And that is where the course utility comes, that if you know a priori that such problems can be solved, then in such forms you are likely to formulate a problem whenever it comes your way. Okay, so this completes our first part of discussion, that was general concepts, general ideas, before we start optimization itself. Next lecture onwards, we will take up the simplest kind of problems, single variable problems. Okay, that will be the starting point in the next lecture. Thank you.